Availability requests should be fast, under 100 milliseconds, to support use cases like search. Ordering should be strongly consistent. Two customers should not be able to purchase the same physical product. Systems should be able to support 10,000 DCs and 100,000 items in the catalog across DCs. Order volume will be on the order of 10 million orders per day. Below the line, out of scope. Privacy and security. Disaster recovery. Here's how these might be shorthanded in an interview. Note that out-of-scope requirements usually stem from questions like, do we need to handle privacy? Interviewers are usually comfortable with you making assertions like, I'm going to leave privacy out of scope for the start, and will correct you if needed. Setup. Planning the approach. Before we go forward with designing the system, we'll think briefly through the approach we'll take. For this problem, our requirements are fairly straightforward, so we'll take our default approach. We'll start by designing a system which simply supports our functional requirements without much concern for scale, or our non-functional requirements. Then, in our deep dives, we'll bring back those concerns one by one. To do this, we'll start by enumerating the nouns of our system, build out an API, and then start drawing our boxes. Defining the core entities. Core entities are the high-level nouns for the system. We're not yet designing a full data model. For that, we'll need to have a better idea of how the system fits together overall. But by figuring out the entities, we'll have the right blocks to build the rest of the system. Problems are everywhere in AI coding interviews. Navigation between waypoints, network packet routing, dependency resolution, social network analysis, and game state exploration. If you zoom out, a surprising number of problems reduce to find a path through a graph, and from there the solution follows directly. Your trusty AI can write any of these algorithms in seconds. What interviewers care about is whether you can spot that a problem is a graph problem in the first place. Pick a sensible traversal, explain to them what the algorithm is doing, and steer the AI through the back and forth without getting lost. Recognizing the pattern. Many graph problems hide their structure inside a described process. Finding the shortest sequence of word transformations, navigating a maze, propagating a state through a network. The interviewer is watching whether you can see the graph underneath. Tells that you're looking at a graph problem. Things and connections between things. Anytime the input has entities and a relationship between them, people and friendships, cities and roads, courses and prerequisites, files and imports, you can model it as a graph. The question is whether you should. Shortest, fewest, minimum, or any path between. These are pathfinding questions. Add weights to the edges, and you're in Dijkstra's territory. Without weights, BFS. Reachability or connectivity? Can X reach Y? How many components are there? Is this network fully connected? These are traversal questions, so BFS or DFS. 2D grids with input rules. A grid is a graph in disguise where each cell connects to its 4 or 8 neighbors. Almost every rooms, islands, maze, or minimum steps grid problem reduces to BFS or DFS on the simplistic graph. A sequence of transformations, word ladders, state space search, and game playing. Each state is a node. Each legal transformation is an edge. Once you frame it that way, the algorithm choice follows. When you spot one, say it out loud before you start coding. This is a shortest path problem on an unweighted graph, so I'm thinking BFS. That's the signal interviewers are reading for. What is a graph? A graph is a collection of nodes, sometimes called vertices, connected by edges. That's it. If you can model something as things and connections between things, you've got a graph. The fact that so many problems can be modeled as a graph is a feature, not a bug. There are a lot of problems that are not obviously graphs that can be modeled as graphs, so you'll get a lot of mileage out of this pattern. There are two standard ways to represent a graph in code, and you should know both because the AI will ask or assume one or the other. Adjacency list. Each node stores a list of its neighbors. This is the default for most interview problems because it's memory efficient for sparse graphs, which covers most real-world graphs and keeps test cases with large graphs from requiring huge binaries. The first code example shows how to define a graph using an adjacency list, where each node maps to a list of its connected neighbors. Adjacency matrix. A 2D grid where matrix at position I, j equals 1 means there's an edge from node I to node j. This is better for dense graphs or when you need O of one edge lookups, that uses O of B squared memory. The second code example shows how to define a graph using an adjacency matrix, representing edges in a two-dimensional grid. In practice, you'll almost always use adjacency lists. If the AI generates a matrix representation and the graph is sparse, that's a red flag worth catching. When you encounter a new problem in the interview, don't immediately think about algorithms. First ask, can I model this as a graph? If yes, figure out what the nodes are, what the edges are, and whether edges relate. The algorithm choice follows from that. Junior candidates often only spot graphs when they're literally in the prompt, social network, or dependency graph. But a lot of the power of a graph representation is that they apply to things more abstract, things like game playing where the edges might represent possible moves. You'll need to be creative in spotting them. Graph traversal algorithms. 4 algorithms cover almost everything you'll see. BFS and DFS for unweighted graphs, Dijkstra's for weighted graphs, and A-star when you have a way to estimate distance to the goal. The right pick falls out of the problem shape, so it's worth knowing what each one buys you. Breadth first search. BFS explores a graph level by level. It visits all neighbors at the starting node first, then all neighbors of those neighbors, and so on. Think of it like dropping a stone in a pond. The ripple expands outward uniformly. This property makes BFS the go-to algorithm for finding the shortest path in an unweighted graph. Because it explores nodes in order of their distance from the start, the first time it reaches any node is guaranteed to be via the shortest path. Starting from the root, BFS pulls one node off the queue, marks it visited, and pushes its unvisited neighbors to the back. Nodes finish in level order. Depth 1 before depth 2, depth 2 before depth 3. The code implements a standard BFS traversal using a queue and a visited set. The key data structure is the queue, which is first in, first out. Nodes go in at the back and come out at the front, which enforces the level-by-level ordering. The visited set prevents cycles from causing infinite loops.
Không có gì đâu, đừng có đi ra đây.
Shortest
Cái cầm kẹo tay có không?
level
Con
order
đi bôi cho nó gái.
will find all nodes within k-hops.
Con cũng vậy.
Any problem that asks for the minimum number of steps. DFS, depth first search. DFS takes the opposite approach. Instead of exploring broadly, it goes as deep as possible down one path before backtracking. It's like exploring a maze by always taking the first turn you see and only backing up when you hit a dead end. The first code example shows a recursive DFS implementation. You can also write DFS iteratively with an explicit stack, which avoids recursion depth limits for large graphs. The second code example shows that iterative stack-based approach. DFS doesn't guarantee shortest paths. The path it finds depends entirely on the order it explores neighbors. So why use it? When to use DFS? Cycle detection. As DFS walks down a path, it can mark nodes as currently on the stack. Bumping into one of those again means you've looped back, which is a cycle. Topological sorting, see the topological sort article. Finishing order from DFS naturally produces a valid ordering of nodes that respects dependencies. Finding any path, not necessarily shortest. When you just need a solution, going deep is often faster than expanding the whole frontier level by level. exploring all possible paths, for example, maze solving, backtracking problems. DFS pairs naturally with the choose, explore, unchoose rhythm, because the recursion stack already tracks where to back up to. Connected component detection. Start DFS from each unvisited node. Everything you touch is one component. Repeat until every node has been seen. Problems with deep recursive structure. If the problem itself is recursive, like trees, nested expressions, or fractal-like state, DFS's recursion mirrors the structure for free. DFS uses less memory than BFS in practice. BFS has to store the entire frontier, which can be huge for wide graphs, while DFS only stores the current path. For very large graphs, this matters. A quick heuristic. If the problem asks for shortest or minimum, reach for BFS. If it asks for all paths, any path, or involves backtracking, reach for DFS. The reason BFS gives you shortest paths for free is that it processes nodes in order of distance from the start. The first time it reaches any node, that has to be by the fewest edges. DFS makes no such promise. It commits to a direction until it bottoms out, so the path it finds first is usually a long detour. When in doubt, BFS is the safer default. Weighted graphs and Dijkstra's algorithm. So far, we've assumed every edge has the same weight. Real problems often don't work that way. In a road network, different roads have different distances. In a network, different links have different latencies. When edges have weights, BFS no longer gives you the shortest path. It gives you the path with the fewest edges, not the lowest total weight. Enter Dijkstra's algorithm. It's essentially BFS, but instead of a regular queue, it uses a priority queue, or minute heap, that always processes the node with the smallest node distance first. This guarantees that when you reach a node, you found the cheapest path to it. The first code example shows the core Dijkstra's implementation using a priority queue. The graph representation changes slightly for weighted graphs. Instead of a list of neighbors, each entry is a tuple of neighbor and weight. The second code example shows this structure. In this graph, the shortest path from A to C isn't the direct ABC route, which costs 7. It's ADBC, which costs 6, because the detour through D is cheaper. Dijkstra's finds this automatically. The key skill is recognizing when a problem is a weighted shortest path problem, and telling the AI to use Dijkstra's. You'll be looking for the priority queue or heap. Then verify the output has the right structure: a heap, a visited set, and distance tracking. Your interviewer wants to see some signals that you know what you're looking at, not accepting any implementations passively. A star, Dijkstra's with a heuristic. A star is Dijkstra's smarter cousin. The insight for it is pretty simple. If you have some idea of which direction the target is in, you can prioritize nodes that seem closer to the goal. Instead of sorting the heap by cost so far, A* sorts by cost so far, plus estimated cost to goal. That estimated cost is the heuristic function, often called h of n. For grid-based pathfinding, Manhattan distance or Euclidean distance are common choices. As a concrete example, if you're at grid cell 2, 3, and the goal is 5, 7, the Manhattan distance is the absolute value of 5 minus 2 plus the absolute value of 7 minus 3, which equals 7. You don't actually know if there's a clear path that short, since there could be walls, but you know any real path has to be at least that long. That's the property A* uses to decide which frontier node to expand next. The heuristic has to be admissible. It can never overestimate the actual cost. If it does, a star might rule out the optimal path before ever exploring it. Manhattan distance is admissible on a 4-directional grid because the real path can never be shorter than walking straight to the goal. Problems with heuristics show up a lot in AI coding interviews, in part because there's often no book answer. A star is a great example of a way to use these heuristics, and they'll show up in other approaches like branch and bound, which we'll cover in the backtracking pattern. This basically means A* is most useful in scenarios where there is some structure to the problem that can be used to estimate the cost to the goal, like if the problem involves spatial pathfinding such as grid navigation, map routing, or robot movement. In these cases, A star will be significantly faster than human Dijkstra's because it avoids exploring nodes in the right direction. For abstract graphs without spatial structure, A star degrades to Dijkstra's because there's no useful heuristic. The code examples show an A star implementation and a heuristic function for a two-dimensional grid where nodes have coordinates. If you have a heuristic or an estimate for the cost to the goal, you should probably be thinking about using a star. Prompting the AI. The move-on graph problems is to tell the interviewer the algorithm and tell the AI the goal. This is an unweighted shortest path problem, so I'm thinking BFS is what the interviewer needs to hear. 5 seconds and it demonstrates real understanding. When you prompt the AI, leave a little room. Find the shortest path between these nodes is better than locking it to BFS, because the AI might suggest something better suited to the specifics, and you want to keep that door open. A few pattern-specific moves. For grid problems, name your reframe. Tell the AI, treat the grid as a graph where each cell connects to its 4 neighbors, rather than asking for a specialized grid traversal. You get a standard BFS-DFS that's easier to read and verify. For weighted graphs, confirm the edge weights. Weights are non-negative, so Dijkstra's works is a useful sentence to say both to the interviewer and to the AI. If you skip this and there's a negative edge, Dijkstra's will silently produce the wrong answer. For heuristic-based search like a star, ask the AI to generate a harness to validate the heuristic. The AI is much better at writing heuristics than verifying them. A small adversarial test set is a high-leverage prompt. If you're uncertain which algorithm fits, say so. I think this is a shortest path problem with weighted edges, so Dijkstra should work. Let me verify that the weights are all non-negative. This kind of transparent reasoning scores better than silently picking an algorithm and hoping it's right. Verifying the AI's code. Graph algorithms are short and well-known, so the AI usually gets the structure right. The bugs live in a few specific places. BFS that doesn't mark visited on NQ. Marking visited on DQ is a classic mistake. You'll add the same node to the queue multiple times and either get an infinite loop or a wrong distance. Check the line where visited.add node lies. It should be right after appending to the queue, not after popping from it. Dijkstra's without the already visited skip. A correct implementation pops a node from the queue and immediately checks whether it's been processed. If so, skip. Without this, you reprocess nodes that get the wrong distance on graphs with multiple paths to the same node. DFS used for shortest path. If the AI generated DFS for a minimum steps problem, that's a structural bug. DFS will time out on anything non-trivial and may not find the shortest path at all. Edge cases the test set didn't surface. Disconnected graphs, target might be unreachable. So does the code return a sentinel or crash? Self-loops, duplicate edges, the graph being a tree with no cycles to handle. The provided test data may not exercise these, but mentioning them out loud tells the interviewer you're thinking past the happy path. The fastest sanity check. Name the data structure. BFS uses a queue. DFS uses a stack or recursion. Dijkstra's uses a minute cube. A star uses a minute cube sorted by F equals G plus H. If the AI's code disagrees with what the algorithm name implies, something is wrong before you even read the loop. When to use versus alternatives. BFS has time complexity O of V plus E, space complexity O of V, and you use it for unweighted shortest path, level order traversal, or minimum steps. DFS has time complexity O of V plus E, space complexity O of V, and you use it for cycle detection, topological sort, exhaustive enumeration, or connected components. Dijkstra's has time complexity O of V plus E times log V, space complexity O of V, and you use it for weighted shortest path, non-negative weights. A star has time complexity O of V plus E times log V, space complexity O of V, and you use it for spatial pathfinding with an admissible heuristic. Graph time complexities are hairy and bookish. Interviewers don't usually drill on them, but knowing the rough shape helps you flag when a solution will time out. BFS and DFS have the same theoretical complexity, but their memory profiles differ in practice. BFS stores the full frontier. DFS only stores the current path. DFS does A star of the same worst case, but A star is faster in practice when the heuristic is good. Neighbor patterns that get confused with graph search. Topological sort is graph search restricted to DAGs where the order of traversal is the answer. If the problem is, in what order can these tasks run, reach for topo sort, not generic graph search. Negative weight shortest paths break Dijkstra's. Use Bellman-Ford instead. If the problem explicitly mentions negative weights, cashback, refunds, currency exchange, don't reach for Dijkstra's. Backtracking comes up when the problem is find all paths or enumerate all valid configurations rather than find a path. DFS is the engine underneath, but the framing is different. What interviewers expect? Beyond the recognition step, which is the biggest single signal, interviewers are watching for. You can explain the algorithm the AI produced. It's BFS, but with a tuple of node and distance, instead of a separate distance map, is the kind of narration that tells the interviewer you understood the choice. If you can't competently explain it, they can't tell whether you got it right or got lucky. You proactively name the edge cases. Disconnected graphs, self-loops, duplicate edges, the graph being a tree with no cycles. These may not even appear in the provided test data, but flagging them shows completeness, and they're easier to spot once you've recognized the graph in the first place. You frame the algorithm choice as a decision, not a default. I'm using Dijkstra's because the edges are weighted in non-negative weights. I'm using Dijkstra's because shortest path. Stating the precondition out loud is the signal. You catch the high leverage bugs. Work on EQ for BFS. The already visited skip for Dijkstra's DFS for shortest path. Leaving one of these out loud while reading the AI's code is the kind of thing strong candidates do. Bring it together. Graph search is one of those patterns where recognition matters far more than implementation. In an AI coding interview, the AI can generate BFS, DFS, or Dijkstra's in seconds. What it can't do is answer the question from the interviewer before hands on a keyboard to realize that minimum number of bus transfers to reach a destination is a BFS problem on a graph where bus routes are nodes. That insight is yours to bring. Practice spotting graph structure and problems that don't obviously look like graph problems. When you see one, name the algorithm, explain your reasoning to the interviewer, and let the AI handle the boilerplate. Then verify the output against the patterns you know. Queues for BFS, stacks for DFS, heaps for Dijkstra's, and A star. That's the workflow interviewers want to see.